Well, welcome to the tutorial session, the last session before we go out and have some beers and forget about everything we learned this morning over the rest of the day. And I'm sorry to be the last one holding you from your point of annihilating all your knowledge. Today's tutorial is writing continuous application with structured streaming. The URL that you actually see up there is the one that you might want to open up in your browser if you want to participate in the labs. It has instructions in how to get a Databricks Community Edition account, which is actually free. Once you have the particular account, you can take it to the graveyard with you. It's going to remain with you for the rest of the life. It's actually a great tool for you to learn Spark and all the other notebooks that are going to be available. Some of the labs they will be doing will be part of those particular community editions. So you might want to open that up in the tab. And while I'm talking, if you're bored, you can probably just log in and get an account. So that's the URL. Did everybody actually get that? Hands up, hands down, lovely. All right, I'm going to make this quite interactive because this is a tutorial, so I want this to be a two-way communication. And if I don't want to answer the question, I'll say I won't answer it. Anyway, so I just want to get an idea of who you are before I tell myself who I am and bore you to death. How many of you actually have used Spark in the last 6 months? Well, you guys can go home then, really. How many of you have used the PySpark APIs? Okay, well, I wonder what you're doing here. How many of you are data engineers? Lovely. How many of you are data scientists? And how many of you consider yourself Python from 1 to 10? Okay, so this course is going to be all about Python because PySpark is an important element for Python programmers, and we have the APIs for writing structured streaming in Spark, so we're going to continue on that. A little bit about myself. I'm currently the developer advocate at Databricks. Previous to that, I was leading the developer advocacy efforts at Hortonworks before I made transitions to advocating knowledge and working with developers and sharing and learning from them as well. I worked as a software engineer at some of the companies here in Silicon Valley for a long time. And I'm also the program chair, so on behalf of the Spark committee, welcome to the Spark Summit, 14th Summit, and I hope you're all having a wonderful, great time, and this will be a memorable one. For how many of these, this is the first summit you've ever been to? Lovely. Well, welcome, and I hope this won't be the last. Okay, a little bit about the company. Obviously, you've been hearing a lot about Databricks. We are the company who actually were the original creator of Apache Spark, and we wanted to sort of keep the trend so that we actually bring the unifying platform for data engineers and data science to actually work together. And the whole idea behind the unified analytics platform is the unification, which you'll actually hear a lot today about the theme, the unified build and scale. The Apache Spark being as a unified engine, why it actually became a unified engine. It wasn't something some marketing genius came up with the term. The design principles of Apache Spark were based on the fact that it was a unified engine right from the get-go. And the things that you heard about today from Reynold were based on those design principles because we wanted to unify things so people can actually sort of work together. So that was the whole idea. That was the whole premise behind that. And in today's talk, I'm just going to give you a very brief idea of what Spark is. I'm sure you guys have known about it, why Spark actually makes sense to write a continuous application. And what does it actually mean to write a continuous application in today's world where data is coming to us in a very rapid manner. And what's an anatomy? What's the footprint? What's the DNA of a continuous application? And then we'll delve down into tutorials. So the idea is that I've broken down into two parts. The first half, I'm just going to sort of give you the introduction of the concepts, and then we'll dive into tutorials. And normally this is a whole day thing, but I've tried to cram it in 1 hour. I hope we can be successfully. But the good thing is that you will have the tutorials with you. You can actually go home and actually work on it as well. And then hopefully we can answer some questions with the pint of a beer when you go out to the party. Okay. You heard about today how actually data has been sort of changing the world, You heard the cliche, data is the new currency, data is the oil. And it's interesting to see how you have to think about data in 2019 and 2020. And I was giving this tutorial at PyData Miami in Miami about a month ago, and I was reading this article in The Economist, the leader, which was making a claim how to think about data in 2020. And data comes to us in raw and dirty. It comes to us in spurts sometimes, or it comes to us in gushes like a tsunami. And it's all just ones and zeros. It doesn't actually make sense. But how do you actually make sense of data? And the important thing is that you can't really make any sense of the data unless you actually have an engine that allows you to be able to process the data, clean the data, put it in a manner, and present it to the application down the stream so that they can actually consume it and garner some insights into it. So the whole idea about writing continuous application is to take these bits of zeros and one and convert them into some digestible nuggets that the streams down the line can actually consume it. Now, there are various architectures that people actually use it. You heard today how data lakes is actually changing that. So that's the whole idea behind that. But then you ask the question, why Spark? There's so many other engines. And I think the case is that right from the get-go, when Mattia and the guys at Amplab were working on Apache Spark, they were trying to sort of address the problem that, yeah, we had all these other engines that actually existed that, but they were sort of bespoke engines. They had their own APIs. They actually had their own MapReduce engines. Hadoop was very much tied to the compute and storage. And the whole idea behind the Apache Spark, which what has become today because of those design principles that Renaud talked about today, was the fact that it's based on these two rich principles. A rich set of APIs, which are built as libraries on top of this core engine, and the unified engine that actually uses what MapReduce used before, but in a very fault-tolerant manner. And once you actually have that core engine, which actually uses the same kind of engine to compute with MapReduce for all these different workloads, you can start expanding things along the way. So you can actually put deep learning pipelines on top of that. You can actually put graph frames on top of that. So any new workload that you actually need that requires processing at scale, the underlying Spark engine can handle that, as long as you actually decouple that and you don't make that core engine very, very complicated. And so this dichotomy, this decoupling actually really was one of the core principles. And it's because of that you saw today 3 principles of how Renaud made the narrative that the Spark started as a big data processing engine. Then we actually wanted to unify that by bringing the new workloads. And then we actually wanted to run it everywhere. And now we actually introduced pandas. So that's the whole idea, is that if you actually look at that top level, they can actually go in a lateral way. And you can put X as one of the new platform over there. And the idea behind unification is really the thing, is that we wanted to be able to, the community and the original creator of Apache Spark, had those core principles. We wanted to actually do ETL, we wanted to do SQL, we wanted to do streaming, we wanted to do batch, but we didn't want to have bespoke engines. We wanted to have one engine that allows us to do that, and we wanted the APIs to be simple, to be intuitive, to be declarative, so programmers and developers like you can actually use it. And as time went by, we started to see that actually came to the fruition. And you saw that this morning, and you will continue to see that in Apache Spark 3.0 and 4.0 and 5.0 and whatever before I die. And obviously, the most recent additions is the ability to actually make these deep learning frameworks as first-class citizens with Horwood as a distributed engine, and the 2.4 introduction of the barrier mode allow us to actually do distributed training in a distributed manner, using the Spark's executors to do all the training in parallel. And this was the evolution. This is history, but I think we have to learn from history. We have to keep that vision in mind if you actually want to go forward. We have to know where we came from. And it was first distributed engine, right? Hadoop was the first class that everybody wanted to use Hadoop. It worked fine. And the problem with the Hadoop was you got all this bespoke engine. If I wanted to use streaming, I have to use a new engine. I have to learn the API. I have to create a cluster for it. I have to learn the learning curve. It just was putting a lot of burden on it. And the whole idea behind Spark was to actually take that and make that as a one engine. And that was the whole idea of unification. Unification, not something. It's not a marketing term. It is something that actually was in the DNA of Spark right from day one when Mattia and the rest of the group at Amplab built that particular thing. And again, I can't emphasize the importance of unification. Simple APIs, because it allows you to actually be very productive as a developer, whether you're a data scientist or whether you are a data engineer, or you're learning Spark. The learning curve is incredibly low. And code reuse, because you only need one engine to do everything. Whether you're doing fault tolerance on that engine for any of the workloads, you actually use your engine. If you were to monitor that, you just write one monitoring script that actually monitors the engine. You get the benefit of writing once. And then the important thing about that was once you actually have a core engine and you have all these APIs that you build on top of that, what happens is that people like you can actually build various applications on top of it. And that's really the power. That's really the power of Spark that has really flourished in the last 10 years. If the Spark wasn't this, I wouldn't be standing over here and talking to you, and you wouldn't be wasting your time rather than being at a pub. This is because of this particular reason. And I think this is going to continue to do that because the people who actually were prescient enough to realize the vision where the trends were going. And you saw Reynold this morning emphasizing the fact that we spotted these trends happening and they reacted to it and the community reacted to it. And all these things actually have come to the fruition. It's because of this. I can't emphasize that. Now, I can see in the crowd a lot of bald heads like me, some gray hair as well. How many of you actually carried those devices with you when you were filming your kids playing football or baseball? You were carrying, like a little geek walking around with your GPS and with your calculator, with your Palm Pilot and all that. And all those were different things that actually did exactly what you wanted to do, but you had to carry all that. And the analogy I like to simplify is that what happened was with the specialized devices, just like Hadoop, you had all these different devices, all these bespoke engines that were actually running. Then came this revolutionary unified platform, unified form called iPhone. And the APIs, whether it's Android or whether it's iOS, gave you a single platform. All these applications had three things in common. They had the screen, they had the data, and they had the internet, right? And they had the APIs. And what happened was people started building applications of it, and it just flourished. And this is actually a great analogy because if you can actually do that for mobile platform, why not for distributed computing? And that was the whole idea behind the Apache Spark having evolution. So I just wanted to sort of share that insight with you, that how actually led that to. Now you're begging the question, Jules, what has that got to do with streaming applications, right? Why streaming applications are inherently difficult? Let me try to elaborate on that. Building streaming applications is difficult for various reasons. In the old world, before the whole idea about structured streaming and before a unified engine, you just wrote an ETL, you took that something and you dumped it to your data lake, you dumped it to your file system, and that was it, right? They existed in isolation. But today, streaming applications don't exist in isolation. They exist in collaboration with a lot of other static applications, a lot of dynamic applications, a lot of ad hoc applications that actually have to interact with the new data that's coming in. Remember the image that I shared with you early on that I told that I read in Economist and it just had the aha moment for me is how to think about data in 2019 and 2020 and it is go beyond with all this deep learning frameworks coming up. It is because your streaming applications, whether you're writing machine learning model, whether you're writing a deep learning application, it's not going to work in isolation. It's going to work in conjunction and in collaboration with all the other applications that are running. And because of that, it's difficult to write a continuous application. And all the good things in life and the bad things in life come in threes, right? They come in threes. Three is the magic number for everything, believe me. Data is complex, right? We know that. Some of you actually have worked with data. Data is complex. Why? Because there are diverse formats that you got to work with, right? You got JSON, you got Avro, you got text, you got binary, you got CSV. You got streaming of data coming in. And data is actually complex. And it's tardy, and it's dirty as well. So you have to deal with out-of-order data. And because of this particular complexity, continuous applications are difficult. So that's one, data is complex. And it's not something I'm sharing with you. Everybody knows that data is complex. The second problem is that workloads, you need complex workloads. Streaming applications, as I claimed earlier, don't work in isolation. They work in collaboration with other things. Because you might have streaming applications with interactive queries. You might have your queries doing machine learning, or you might have some static data that you're actually dealing with. So your complex workload have to be able to handle not just streaming, but all the other things that you actually work with. And as a result of that, data is complex, and workloads are complex as well, because you need all those combinations. And the third is the systems that you're going to be dealing with, the data sources from which you're going to be reading data from or writing data to, have system failures, right? How do you deal with that, right? how do you deal with an application that continuously running and some aspect of it actually failed? You have to recover from it in a very fault-tolerant manner. So because of this trilogy of complexity, data applications are, or streaming applications, or continuous applications. And what I mean by continuous application is applications that are running in a continuous manner where data is coming in real time, and you're either transforming it, you're either writing to something else, some other application down the stream is consuming that cleansed data in order to answer queries or garner insights or make inferences or update certain dashboard is the whole notion behind continuous application, the word continuous. And so how did we actually solve this particular problem? Or at least how does Apache Spark solve the problem? And it turns out that the reason we actually went with the structured streaming is because of the fact that we had built our first iteration of the Spark SQL engine, which was very fast, which was fault tolerant, and so you could actually, your Spark jobs could actually fail, and you could pick up from where you left off. And the DataFrame APIs were actually built on top of that. So that sort of allowed us to be able to say, okay, we can actually run applications in a manner that if they fail, we can start where we began, and we can continue doing that. And this was because of the fact that we can actually handle all the different complex loads. Remember my second diagram where I actually referred to the arrows up at the top, which were the APIs. Because of that past experience, we actually used that to say we can actually handle complex workloads because we have APIs for machine learning, for graph processing, for SQL, and for ETL to be able to do that. And so because of that unified APIs, we can handle the second problem, which was the complex workloads, all right? And the third was built on first and second is because of the Spark's data source APIs, which sort of allows you to write connectors to external systems so you can actually read data and write data in a fault-tolerant manner, gave us the ability to deal with data sources or systems that actually fail periodically, and that way we can actually handle those. And the whole reason behind this was that you, as a developer, when you're writing a structured streaming application or a continuous application that interacts with other, you shouldn't have to reason about streaming at all, right? If you think about streaming as nothing but a table that grows continuously within the physical bounds of nature, a table that grows continuously, and you would query the table just as you would query a static table with your DataFrame APIs or with the SQL. And that was actually the whole point. And you don't have to reason about what about if it fails, and you don't have to worry about the fault tolerance, and you don't have to worry about dealing with data source APIs, you don't have to worry about all tolerance. Let the engine take care of it. And the model was incredibly simple. As Alan Kay says, simple things should be simple, and complex things should be simply possible. And the whole idea behind this very simple model is that all the data that actually comes in structured streaming, we just treat it as an unbounded input table within the physical constraints of memory. And as new rows come in, we just append the table. And you start sort of querying whatever you actually want from top to bottom, right? Your queries are just dealing with old data, and if new data comes in, the same query will work against the new data, and will update any results in the old data if any new data comes in that actually requires some aggregation to be updated. And that was actually a simple model. But it conceivably complex, right? The whole idea behind simplicity was to be able to actually give you the API so you can actually write that and let Spark handle that. And then that was the premise that you write the queries and let Apache Spark deal with that. In other words, let Apache Spark streamify that. And what does that mean? Now let's take an example, right? I promise you're going to see lots of code. Here's a very typical Apache Spark that automatically streamifies, and I'm using this verb streamifies, which means that it actually incrementally takes your query and executes on the new data that actually comes in. And the streamification is an incremental execution. And the reason we could actually do that was because the Spark SQL was built on taking your query, creating a logical plan. Once you actually create a logical plan, it actually creates a very optimized plan. And then once you actually have a physically optimized plan, which you have written in a high-level DSL language like DataFrame APIs, and it gets physically converted through the catalyst and through the whole-scale tungsten generation to a very optimized RDD execution plan. And now you can actually incrementally execute that on your table, which is infinitely growing. And the timeline is what at T1, you will have the same query executed on the new data. At T2, you'll have the same query executed on the second batch of data, and all the way to Tn. And this incremental execution sort of allowed you, or as a developer, to think about, streaming is coming in, I'm just going to create it as a data frame, and I'll just query the way I actually want it. And if I'm doing aggregation, I'll just do aggregation count, as I would do in my SQL static table, and Spark will actually automatically do that. And that was actually the beauty of the simplicity, right? That's what it was. The streamification means that I'm going to take your query. It's very simple. I'm reading a stream from Kafka, and I'm saying, go ahead and take my input device, and I'm doing some transformation over there, and just filter out all the signals which are greater than 15. Now, signal greater than 15 could mean anything. We just hypothetically think that the signal is greater than 15 is fine. I'm going to write back to my parquet and put it in my destination table. So later on, anybody who actually wants to read that can consume that in real time, right? Because you're actually processing this and writing this on incremental phases. And those queries, as you see on the left-hand side, could be written in DataFrames and Datasets SQL as well. And that's the simplicity of writing a continuous application, even though this is a very simple case, but I'm making an illustration, making a case that was, the reason this is possible is because the underlying engine allows you to actually do that. Whereas in DStream, which was a predecessor to structured streaming, you had to deal with a lot of fault tolerance. You had to deal with backbashing. You had to deal with state management. You had to do all that by yourself and become extremely cumbersome, right? I mean, when I was doing that, I was getting a nervous breakdown. But that's a lot simpler. Now, currently in structured streaming, there are two processing modes. In 2.2, structured streaming was introduced in 2.0. In 2.2, we made GA. And since we made Spark 2.2 GA, almost a lot of people in production are actually using the structured streaming at scale. You probably heard about that with Michael Ambrose today, and Apple is using it, Riot Games is using it. All these customers who are actually using structured streaming at scale. So there are two modes of structured streaming. The default mode is the micro-batch processing. And the continuous processing, which was introduced in 2.3, is experimental, which means that Spark has jobs running continuously that as soon as data comes in, I'm going to process it right away, right? Now, you might say, well, Jules, isn't micro-batching bad? Why is it micro-batching? I would contend that everything in streaming is really micro-batch. Think about it. If you're writing, how many of you are network programmers? You've written network applications. Remember, when you write a network program in C, you actually created a file descriptor, you create a socket, and you do a select on that socket, and the socket will block, right? It will block until data comes in on the particular socket, and then you get a system interrupt, and you'll jump into your user application, it will read that socket, but where does the data go? It doesn't go straight to your application. It goes in the network buffer, which is part of the operating system, right? It's buffering the data. You're not seeing it right away. You will see it when your buffer is full, and the kernel will give another interrupt, and now your application will get the data and will actually read it. So micro-batching is not something that's bad. It's happening everywhere, but it's just completely hidden from you. You don't see that. Whereas in continuous application, there's no notion of triggers. You actually have a job running continuously, just like you would actually have a job running on a socket where it's just waiting for data. As soon as data comes in, it'll start reading it. And all the state management and everything is actually handled by the underlying structured engine. So those are the actually two modes. Now, depending on your latencies, you might argue, which one should I use? And we have done some data analysis, we've done some benchmarking, we've talked to a lot of customers who are actually using the structured streaming mode. If your latency is within, say, 50 to 100 milliseconds, which is not unreasonable if you think about it. Even if you're dealing with fraud detection, 50 milliseconds is reasonable to actually flag something that seems like a credit card. You could use structured streaming, right? The continuous mode is as soon as the data comes in, boom, we process it right away. So you actually have on each executor, you have a process running that's just like pinging the the source. And the source is where the data coming, whether it's a file system, whether it's a socket, whether it's Kafka, whether it's Kinesis, it's continually pinging that to do that. That's continuous processing. So those are actually two modes. And to look at closely, the structured streaming actually, when you actually have micro-batching, what it actually does is that there is a task created on each and every executor is actually reading that which task. As soon as the task is over, it's actually gone. And then it keeps track of that in the Spark driver. The Spark driver keeps the metadata of where you actually have read and how much data you read and where in the file system. Or in the case, if it's Kafka, then what topic you read, what the partitions were, what the offsets were, and it keeps track of that. The executors keep track of write-ahead log that actually says what data I've actually read. So if it actually fails, I know I can talk to my driver and say, can you tell me what was the last thing I did? And it'll tell you read from this particle, you failed, you didn't tell me to update that, so I'm going to give you the same things, go read that. And that's how the fault tolerance was done. Whereas if this was a continuous mode, there's no notion of epochs. You actually have a task running continuously on each and every executor, and it's continually polling. And that's what you actually normally do when you write socket programming, right? You're actually polling. You're polling on the socket descriptor. And if nothing fails, the process is just going to block, right? And you will only read when the kernel sends an interrupt, and you read that into the network buffer, and then from the network buffer, it gets passed on to your memory. So those are sort of the two processing mode, right? And this is sort of at the conceptual level what it is. Now let's look at a footprint of what a continuous application looks like, you know? What is an anatomy of a continuous application? And let's take an example of a simple ETL, right? A simple ETL with streaming word count. And its word count is something you probably never heard of. What's so funny? No, I mean, you know, word count is your quintessential example of hello world, right, in distributed computing. And so let's just look at what we'd actually look like in structured streaming. And it's a simple example, and I just wanted to share with you the anatomy of what the query looks like. The step one is you will always going to read something from a sink, right? That's your first step. You're going to specify what the sink is going to be. So I'm going to read my thing from a structured streaming. The option is I'm going to subscribe because I'm reading, and the topic is input, and I'm going to load that into maybe a data frame. So the first thing you can do, specify the source, read from one or more locations if you have more than one topic, whether you're reading from a file system, and we support sinks like files, Kafka, socket, which are actually all pluggable. You can actually write your own sink, the APIs that you can actually extend it, but the supported one out of the box is files, Kafka, socket, Kinesis, and then there are a lot of other, you have people who actually write connectors that plug in very easily because the data source APIs are very extensible. And I don't know if you actually attended today's developer talk by Ryan Blue from Netflix, who is actually writing the data source V2 version that allows us to do both batch and streaming at the same time. It's a new version of API which will come out in hopefully as a developer release in Apache Spark 3.0 that Reynolds pointed out to this morning. So step number one, you're going to specify a source. And then the second thing you're going to do, you're going to transform, right? And then, as you know, in Spark, some of you are conversant in the DataFrames APIs. You use the high DSL operators to do your transformation. Over here, we are just transforming, taking group by, taking the value, and we're casting that as a string and putting in the key. Now, we'll get to what does it actually mean, group by value. So when you read something from Kafka, you get a big data frame, and then one of the columns is the binary version of the blob, and it might be a JSON. So we're going to cast it as a string. And this just happens to be, a word. And then we're going to aggregate that as a value. And once we that, we have done our transformation. So this is going to be run continuously, right? The aggregation is going to be counted. So step number two, you do your transformation. What do you think the step three is going to be? Thank you. You're going to write it to a sink. Right? You're going to specify your sink, where you want the data to go to, how often, and where do you want to go to. So you specify where you want to write this data to. And the supported sinks today are equivalent to or the same as the ones that we support for input. So you can write it to a file. You can write it to a Parquet. You can write as an arrow. You can write back to a Kafka after you made the transformation. And if there is another job running down the pipeline that's reading from Kafka topic, it actually has your transformed data, and it can do whatever it actually wants to it. So that's the whole idea. You can actually build these streaming pipelines with this particular notion of the continuous application. And then part of the sync, or part of the step 3, is that you want to specify the different kinds of output mode that you want to tell Spark to compute. And there are a few ones that we actually support. There's a complete mode, which means that take everything and write everything out, including the new one. The update mode is you only update the ones that are new, that actually come in, right? That the old one has been updated, the new one. So update that. And then there is the append mode, which means that just have the new ones. And then finally, the last point, and a little bit more, is the trigger. And the trigger is, if you recall, when I was streamifying data, the trigger is how often do you want these to be executed? How often do you want your query to be incrementally executed as the data comes in? And over here it says, I want the trigger to be 1 minute. So every 1 minute, whatever the data is being accumulated, I'm just going to go and execute my query. And then more data comes in. The next time clock goes in, I'll do that. And time goes on continuously until something blows up, right? The output mode is update, and then I'm doing a checkpointing. And the reason you want to do a checkpoint is for fault tolerance, is because you want to be able to instruct the driver and the executor to say, how often do you actually do a checkpoint? Where do you want the checkpoint? So the state is maintained. So that way, should something happen, I have a write-ahead log. I have a log that I can actually go to find out where I stopped, what I wrote, what's new, what's old, and I can just continue from there. So that's the checkpoint part. And then you just execute the start on that particular query. And what comes back is actually a handle to an object called streaming query, and then you invoke the start. Now this is a very builder design API that you just sort of use dot methods. A lot of people, if you're dealing with high-level programming language, you just use those particular methods. Very easy to read, very declarative, very intuitive, but a lot of things are actually happening under the covers, and that's the whole reason behind easy to use APIs, so we can actually make developers very productive. And just another more illustrative diagram of what complete mode means is that when you actually have, if it's the current state of the complete mode, if I have a new batch comes in, I'm going to write everything plus whatever the new has come in. If it's update mode, I'm just going to update, for example, the rate dot that has been modified. And if it's append mode, I'm just going to bring up the green, which is the new one. And that's what actually means those distinctions. And normally when you're doing debugging, it's actually nice to actually have complete mode. But complete mode might be something that you actually want to do. For example, if you are looking at clickstream data that's actually coming in, and you actually want to find out what are the top 10 sites that people are actually visiting. So complete mode would be something that you actually want to use, and you just say, give me the first top 10, or give me the top 100, and so on and so forth. And this is something a little more about checkpointing. You do a trigger, you do a checkpoint, and then there's a last bit about the anatomy of an application is this notion of watermark. And the watermark is saying every event that Spark receives from a Kafka or from a streaming, there's an event time associated with that. And the event time is a timestamp at the time when the event happened, not at the time when it arrived in the system. Structured streaming deals with that particular time, which is the event time. And obviously, remember we actually had the checkpoint. You want to somehow keep a state. At some point, you want to drop the data if the last end time of a window that you actually see has passed more than 2 minutes, you drop that particular data because there's no need to keep on maintaining data, right? Otherwise, you're going to run out of memory because you don't want to keep the state of 3 days. So watermark allows you to put a threshold by saying if the data has come in too late, right, then just drop that. In this, I'm saying if the data is 2 minutes late from the last event time that actually saw from the last event, if it's 2 minutes, the old time came in out of order, I'm just going to drop that. And this is just some idea about checkpointing where the executor and the driver work in sync where they actually keep the the write-ahead log to ensure that we can actually do that in a continuous manner. And this is mainly for the fault tolerance, which was the second part of the complexity that we're dealing with. How do you actually deal with fault tolerance? And that's a very good reason. So that was word count. What about things like the new kinds of ETL? As I say, streaming applications don't happen in isolation. They actually happen in a lot of things. And this is a very typical traditional view of how you're actually going to be doing ETL. You got loads of data coming in, streams, ones and zero. They come fast in seconds. You take it from the stream and you dump it into a file, right? You heard about Mike that was talking about the Lambda architecture. And then you have after Lambda architecture, you take hours of processing and you're going to dump into some SQL table. And then down the stream, you actually have applications that are going to consume that. You might have an SQL ad hoc query, they're actually doing it. There might be a web application. There might be machine learning, right? But this doesn't really work in today's world in the continuous manner because data is happening in real time and you want to be able to react in real time, right? And so the problem over here is that data comes in sometimes dirty, semi-structured, so you actually want to do an ETL right away, and you want to have the data ready to be consumed by the processes down the line. Periodic jobs can actually fail, so you actually want to make sure that the data is actually structured, that actually goes in. And this actually creates a problem because for applications that actually require real-time response, this is unacceptable, right? You just can't do an intrusion detection 4 hours after your network has been attacked, or you can't do fraud detection if the downstream application is late. And so that was sort of the traditional way. The new way of doing things with structured streaming is that your data is coming in, you modify it, and you write straight to the table, if table is the last sync that you actually want. And then everything mostly actually gets within your 50 to 100 milliseconds real-time data. The downstream application can actually take that. And that's fairly acceptable, right? And that sort of changes the equation, right? Eliminate latencies because now you don't have to deal with hours. You're now dealing with milliseconds. And you get the sense of immediacy, right? You're actually dealing with almost data that comes in real time. And it transforms data continuously because we are dealing it in a continuous manner. Data is coming in, I'm transforming, I'm writing it. Data is coming in, I'm transforming and writing, and somebody else is consuming it. The alternative would be instead of putting in a table, you actually put in a data lake that we talked about this morning, that Michael gave an introduction. Now it's actually open sourced. And so once you actually put in Delta Lake, you actually have an incredible reliability of data. You can do all the things that Michael talked about in terms of the ability to go back in time. You can do schema enforcing. You can do all the great things that you actually had to do very much manually, but now you can just dump things in Delta Lake. You got schema, it's on Parquet, you build tables on that. And it gives you an incredible flexibility. And you get all the benefits of Delta Lake if you chose to do ETL going the other way, right? So that sort of is the new way of how you write continuous streaming applications, to be able to take handle of streaming coming in and writing it to a data lake or to a particular Parquet table that other other applications can get to it. So let's look at the ETL now in the new world. Very simple, PySpark, very simple. You just import the trigger that you actually want from PySpark. You read the particular stream from the Kafka. If you have multiple servers that you actually read it from, you just actually read from there. You subscribe topic, you load that, and then you do your transformation. Right? And then this transformation is a DataFrame API, right? You can use the DSL to do expression, cast the value of a string and put it on JSON. And JSON is the value of that your IoT devices might have created, and it's now sending into a Kafka stream. And then from that part of transformation, you can actually use the structured streaming APIs that we provide as built-in utilities. They take from JSON, use the schema that I'm going to give, and then create this particular column called data, and then select everything from data. Data.explode is going to explode that particular column. Once you get the parsed data, do a checkpoint, partition by date, because I might have a query down the line that I want to partition by date so I can do some time series analysis, or I can make queries based on certain time, or I can do time travel as we heard about. And write it as a Parquet file. Here's my trigger. And if I wanted to write to Delta, all I do is I just change it to Delta format. Now I'm writing to a Delta Lake. Right? Just one line of code. And you're writing it to Delta Lake. Whereas before, you're just writing it to Parquet. And Delta supports Spark. But when you write to a Delta, you get all the additional benefits of the reliability, the ACID transactions, the time travel, and everything you actually have. And then that's your place where you actually want to start writing to the location. And I alluded earlier that when you actually read something from Kafka, what you actually get is this huge data frame, right? And these are the columns. But what you care about is the value. Remember, I was looking at the value, and I was transforming it that. The rest of the stuff is mainly for Kafka partitions, what the key was, what the topic is, what the partition is. And this is offsets, and all this is actually kept track of by the executor and the driver, so that the driver tells the executor, read this particular offset, read this offset, and then you can do the aggregation. And if you look at the JSON data, when we use the cast value and when we did the select from, those are built-in utilities. All they do is they take your JSON data, and when you do from JSON, go ahead and explode that. What you get is now the actual data frame that has your columns in it, and then you can start doing your transformation on that. And these are all built-in utilities that you can actually use. And if you're actually interested to use those particular APIs, I have these 2 blogs. The slides are, by the way, available on that tab that I gave you. You can actually look at those, and I've got a few notebooks that actually tell you how to parse your structured data. Your structured data might be very nested, right? You might have data frames embedded, a JSON within embedded. You might have arrays. You might have structured data. And these APIs allow you to sort of deal with complex data. And if I wanted to write to Parquet, I can do that, or I can actually write to the data. So that was sort of introduction to the complex, some concepts leading to continuous application. And what I want to do now is switch to tutorials. How many of you are actually interested in the tutorials? And the rest of them want to go home? Just kidding. Okay. Yeah, go ahead. Where is it? Here? Well, I mean, the format is okay, right? The trigger is just telling that when you're writing it, after you process that, I want this trigger to be executed at 1 minute interval, do the transformation, and then write it to Kafka.
My question is, with the trigger set to 5 seconds, we're reading from the Kafka stream, let's say. So is this, we didn't write a while loop there, so is this still a continuous?
Yes, it is a continuous. Do you see the start? At the end, this particular thing over here? This thing here? Oh, you don't see it. Oh. Hey, that's the start. That actually runs continuously. Right, and what you get back is a query handle. And once you get a query handle, you can actually write a job that query.stop. It's like, it's like socket.close. This is query.stop, and then it's going to kill that particular job. Yeah? Yes. You actually want to use, if you're running in the cloud, you probably want to put it in an S3 bucket. You don't want to put it on temporary file system, because if your executor dies, then you don't have the checkpoint, right? So normally, most people actually put it on some bucket location that's, AWS or Azure actually has fast file system where you can actually write effectively. Or if you have an NFS mount file system that's accessible, you can actually do that. Any other question before we go to tutorial? Yes?
I have a question about error handling. So as we introduce Delta, there's schema enforcement.
Yeah.
What are we going to do about streaming data that's coming in as corrupted?
Streaming data is coming in as Spark?
With violation of the schema.
Oh, the violation of the schema. Now, when you specify read it using this particular schema, the options you can actually specify in the read data reader that's saying, if it's bad data, write it over here. if it's how tolerant you are about data handling. Right? If you want this to fail fast, which means that if if it's not compatible with my schema, end the process right away. If the column item is actually missing, just put not an integer, not a number, or put some value associated with that. So there are all these different options that you can actually specify in reading from a data source to saying how do you actually handle if it doesn't comply or doesn't conform with the schema. 3 things you can specify. You can either say fail right away, or you can say go ahead and run it and just put some garbage in it, some value that you think that you can parse out, or just ignore it.
Is that a part of a feature for Delta or structured
No, this is
streaming?
part of a feature of data source, right? The Delta schema is something else, but yes, it is actually related to it.
Okay, thank you.
Yeah.
So we have about 100 topics on there. So the data is coming in topic.
And reading from 100 topics.
Yeah.
Wow.
We want to create a streaming job.
Yeah.
Each of the topic. So it will become like 100 streaming jobs. So can we host in using one driver, can host this 100 streaming jobs?
Well, I mean, if you're going to be running, the whole idea behind writing continuous application is the reason you're using Spark to write continuous application is you want to take care of distributed jobs. Now, even though you actually have 100 topics that you're reading from, the 100 topics are going to be read in parallel. And it's not the same data it's going to read, because every executor is going to read from different partition, different offset, because the driver is going to say, okay, you read from here, and you read from here, and I'm going to keep track of who is read where. So next time if something goes wrong, I can direct and dictate and guide the executor to say, start from here, because I didn't get an update from you that you finished reading it. So your question was
Independent jobs, right?
yeah, these are independent jobs.
So can I host them, because we are under Docker container.
Right. Can
Can we host them as one master container, one driver container that actually spins?
I mean, the driver, as the name suggests, is one of the most lazy person in the world, right? It just dictates, manages everything, right? So you do this and you do that. It doesn't, and you don't want it to do the work. You want the executor to do the work. That's the whole idea behind that. And the driver sort of, it's like a bin counter. It says, I'm counting this particular bins. It's like I've got marbles and I'm going to count. I'll keep. Yes, you can. Well, yeah, you can launch from there. The driver is responsible to launch everything, right? Because if you do a Spark application, the driver is going to create a DAG for you, and it's going to work with the DAG scheduler, and then it's going to. Oh yeah, you can use 1,000 jobs, yeah.
So when I tried before the Python API for Spark, it was not as rich as like a Java Scala. It's been like more than a year back. Is it as good as?
Yeah, I mean, all these particular APIs. Oops. All these APIs do compile to the logical plan. So if you stick to the API, whether you're writing in R, whether you're writing in Scala, whether you're actually writing in Java, whether you're writing in SQL, they all go through the same journey. So if you stick to the APIs that we actually provide, the code is equivalent, right? It doesn't really matter. Now, if you start putting lambdas and all the other stuff, then we can't guarantee the performance is actually the same, right? Okay, last question before we actually get, yeah. Yeah. Yeah, I mean, it's a rotating log, right? You actually keep, there's a timestamp, there's another job that actually runs it. It actually gets bigger, it gets chopped into smaller logs. Now, one of the great things that actually Delta does, which Mike talked about today, is that how do you deal with all the small files, right? Because if you have a checkpoint that's very frequent, then you're going to have all the small file problems. And then you got all this metadata sitting there. How do you actually scale that? And Michael addressed that the way we actually doing that is the ability to do what they call vacuum, which does the compaction, right? Now, today you can do a compaction by having an asynchronous job that actually runs and does the compact. But this is actually happening as part of the Delta job that's actually running. You say, well, the file has become so big that I'm just going to compact that. But that actually happens in the background. You don't have to worry about it as much. But you can specify that, Yeah. I mean, you have to account for storage, obviously. The thing about continuous application is that if you're going to be reading data continuously, you want to somehow have an idea of first what you're tolerant, how tolerant you are in terms of late data out of order, right? The second thing is that how often do you want a checkpoint? And the third thing is that what is your watermark? Is it 1 minute? Is it 5 minutes? Is it 5 hours? If you're doing IoT devices at the edge, you don't care. Right? You might want to do it every 2 hours because sometimes the data comes in trickles, and you want to be able to handle that, right? Because if you're at the edge of the net and somebody is doing a push on the Kafka, normally, for example, to give you an illustration, if you are an oil rig somewhere in the North Sea, and your mothership is in Dublin, and you got all these oil rigs in the North Sea, and they're sort of collecting data on an hourly basis, and at the end of the day, they talk to the mothership in Dublin, and they send the stuff out, right? But you somehow want to say, okay, my out of order, my watermark is 24 hours. So if I receive something, after 24 hours, I don't care about it because the data might be corrupt. I don't care. Okay, so let's go on. Did you guys? You see my screen? Let me go ahead and start this particular cluster. Okay, did you get this particular? Oh, you didn't get the link. That's the link. Yeah, once you open that, all the instructions are in there. Can I move on? Okay, brilliant. Okay, so now if you want to run this, how many of you actually want to run this in Databricks, or you just want me to go through the notebook because we have about another half an hour or so. You guys want to do it in the Databricks? Okay, so let's go ahead and do that. Did you go to this particular link? Let me just open that up. Yeah, go to this particular link over here and sign up for Databricks Community Edition, right? Once you sign up with your email address, make sure that you don't have a VPN turned in. You'll get an email address that says how to actually log in, right? Once you actually log in, use this particular URL, use your credentials to log in. And once you log in, what you'll get is something like this. This is the Community Edition. The Community Edition is actually free. Think of your Spark running in local mode, but in the cloud. This is for you to learn to run notebooks. It's limited. You can't run multiple jobs. Just one driver, just one container, and you got 8 cores and enough memory to actually do a fairly reasonable job for you to actually learn Spark, even do continuous application. So how many of you have actually logged in over here? Yes! Ha! Love it. Okay, the next thing you're going to do is that, see this GitHub URL? Cut and paste that. And go to your browser, go to your Community Edition. Workspace. Import. Okay? Now, before you do an import, I want you to download that. So take that particular URL. And this is in my GitHub. Download that. And you'll get the DBC file somewhere on your download directory. Right? Once you actually get that, you go back to your Community Edition. You do an import. Browse, pick up this file, open, import, and it will actually create a folder for you by that particular name, and you'll have all these notebooks in there. Did you get it? How many of you have actually done that? Yeah. Yeah. Oh, you got it. Okay, lovely. All right, so I'm not going to use the community edition. I'm going to use the Databricks one. Why? Because I got the mic and I can afford it. No pun intended. I'm going to get in trouble, you know. All right, so I'm going to use my, my continuous mode. And the next thing you want to do is you want to actually go ahead and create a cluster. So go to the workspace. And create a cluster. Now, if everybody's going to create a cluster at the same time, we might start spinning. But you have to be on the net, obviously. And just type in, you know, my tutorial cluster, and choose, as you see in the worksheet, 5.3 with Scala 2.4. Choose that particular runtime, and then go ahead and create a cluster. Yeah. Sorry? What's the purpose of the cluster is where you're going to be running the notebooks, right? You got Spark install, you got a driver running on there, and you got your workers running on there. Now, because this is a local mode, how many of you know what a local mode is in Spark? In Spark local mode, you actually have one driver. It's like Spark running on your laptop, but this is running Spark running in the cloud in the local mode. And local mode is actually incredibly good for getting started and learning Spark. Right? So we wanted to actually create this as an educational tool. So when we give actually workshop, you get a flavor of what is it like. And it's a great learning tool for those people who are actually getting started. And you can do some really complicated things, right? And it's free. We're paying for it. And so it's a great tool to learn. If you want to learn Python, if you learn Scala, you know, you just create a particular notebook and start typing stuff, and boom, you're ready to go with it. All right, so everybody created a cluster? Brilliant. I love this group. I can tell why, because everybody raised their hand, they have no Spark. All right, the next thing you're going to do is that when you click on this particular notebook, you will get that, and you see this particular window over here? Go ahead and attach your cluster. If it's solid green, which means the cluster has been created, so go ahead and attach the particular cluster. So I've attached my cluster. That's running with 91 gigabyte file, like about 12 cores, and this is really running in a distributed mode. You'll be running everything on the driver, which is fine for the purpose of tutorial. And I know just warm up the cluster, give him some nice tea. It's about tea time right now. And I'm going to run this particular command called run. And run, %magical command run is any shell scripts that you actually might have, or any other notebooks that you actually want to have. You can actually run that as part of your notebook. So in my setup directory, I have the ability to set up my data. So I might want to mount something from a bucket, or I might want to authenticate something to make sure that. So this is like a pre-processing thing that you actually do. So I'm going to run that. Are you guys doing the same thing? Okay. So this is going to say it's going to mount my data on top of my file system. So I've got all the streaming data that's actually come in. And we're going to simulate, we're reading things from Kafka. The reason we're going to do that is because I don't have Kafka set up, and we just don't have the time. Normally this is done for a whole day, and we set up all those things, and it's actually fun. But it's okay. You get the same kind of behavior as if you're reading from a file system. But we will pretend that we're reading from Kafka, and we'll do that in a continuous manner. Okay? And the idea over here is that, this is repetition. This is the traditional way of doing streaming. One job, transformation, write it back. That's all. The continuous manner is the ability to actually do that. And this is how you actually provide the sources. These concepts are something you can actually read it later on as you go home. And syncs is where you actually write data after you've gone through the processing. And so the next thing I'm going to do, obviously, here is to set up some output data where I think we want to have an output path set up. That's where my streaming data is going to be written to as Parquet. I have a checkpoint directory where I'm going to checkpoint things as time goes by. And then the DBF utils are the Databricks utils that looks like a file system. So people who come from the Unix background, have a look and feel or intuition of, oh, I'm going to do an LS, so I'll look at my files. Remember, S3 is not a file system. It's an object store. But DBFS, I mean, the Databricks file system is written on top of that. It actually simulates, so you get the same behavior as if you were dealing with the file system. So these are sort of utility commands that say in the DBF, go ahead and remove my checkpoint or override my checkpoint if I had some checkpoint before. So that's what this particular command does. If I have any bad records, and I think there was a lady who asked me about, yeah, if you have any bad records that does conform with the schema, you can put them in here, and then later on you can actually find out, what was wrong, right? So that's your question to your answer. You can actually provide that in part as one of the arguments to the streaming data to say, hey, if it doesn't conform with the schema, dump it over there. I'll deal with it later. All right, so this is just some bookkeeping we're actually doing, so we're going to do that. And then, you might want to say, well, what does data look like, right? I've been asked to write this particular streaming job, and I'm reading something from Kafka, but I really don't know what the data looks like. So normally, this is a very typical exploratory phase for a data engineer to say, okay, before I write my pipeline, I don't know what I'm dealing with. I have to somehow get a handle on that. And so I'm just creating this directory called sensor path where my data is going to be. And I know all my files are going to be prefixed with streaming sensor file 1.json, file 2.json, so on and so forth. So I'll just go ahead and sort of string that together. And I can use this DBFS utils to peek into what my data looks like, right? So then I have an idea what it looks like. So I'm going to go ahead and peek over here and say, give me the first 233 bytes. And lo and behold, yes, I have some streaming data that's coming in as JSON. And I got my timestamp, which is my event time. And I have my, see if this works. Oh, brilliant. All right. And I have my timestamp. I have my device ID. I have my device type, because I might have more than one device that's actually coming in. And I have my signal strength, right? So this way, something, if you're doing IoT devices in the edge or in the factory or in the rig, you probably want to send signal to saying my battery might be low, so how strong is the signal? And that's actually a good way to do that. And then I'm going to define my schema. Now, normally, I think it's a good idea, it's a good data engineering practice when you are reading large amounts of JSON file, or if you're using large static file in gigabytes or terabytes of data sitting on a file system, there are two ways to read that. One way to either specify the schema, or the other way is to tell Spark to infer the schema. Inferring the schema is okay for small files, because what Spark will do, it will create two jobs. It will read the header, and then it will read one entire partition to figure out what my schema is. And it will try to deduce, the first is a field, which is an integer, the second one is a timestamp, the third one is a string, and so on and so forth. And I'll try to create columns by that particular name, and I'll just arbitrarily assign the column names if there is a header associated with, if it's a CSV file. If it's a JSON file, then I'll create the names by the attributes specified in my JSON files. If I have an attribute value, then my attribute is going to be a column name. But if it's a huge file, then we advise, at least common practice is that you define a schema. Now, PySpark, like Scala and like Java, has this built-in functions that allow you to define the types Spark understands. And there's a mapping between Spark types and the native language types. There is the particular mapping. You can think of Spark really as a compiler because it's got its own different types. So I'm saying, okay, my schema type is going to be my structure type because I know it's a JSON file. And my structure will have the first entry is called a timestamp, the third device, type, and signal strength. Now, the order doesn't matter as long as it matches, right? I'm saying my timestamp is a type timestamp, which is Unix timestamps in epoch. My device ID is a long type, and my device strength. And then since I'm going to be doing my transformation, I'm taking this particular file, and I'm going to dump it into a Parquet file. And when I write that out to a Parquet file, I want to transform what I read with two additional columns for something down the line that I want to process. And I'm going to include two new columns in there. One is called input file. So I want to know what input file that data actually came in from, right? For posterity, for provenance, and for governance and so forth. People want to say, well, I got this device ID that came in. I want to find out what file actually came in, mainly for reading and audibly. So I have this input file call, and it's going to be like stream time. And then I also want to see, at what time did it actually hit my system, called processing time. Just, again, we're just doing it for posterity or for our own calculation. Remember, everything in structured streaming is based on the event time, which is the timestamp that you actually saw when it came in, not on the process time. So that's the particular schema. So I'm going to define the schema. Very simple. So that's my particular schema. Now I'm going to do the beautiful job of saying, okay, now let me start my job reading my stream from JSON. And what I've done over here is, this is really packed, so let me just go through line by line. All right, this part over here is my schema that I defined above. Agreed? The second one option, the max file trigger 1, what I'm saying over here is that when you're actually reading from the file system, read one file at a time and read only one file at a time and look at the M stamp. And this is like simulating as if you're reading from Kafka, right? And I'm slowing it down one file at a time. I can say read file at a time, but I'm just saying one file at a time for the sake of demo, which is like as if it's simulating that I'm reading it from a topic. Now, this would be a Kafka topic over here, and we just read the data. But over here, I'm reading from a file system, right? And then if any bad records that I have that doesn't conform with that schema, just go ahead and put that in this particular path. JSON sends the path. That's where my data is. And then add this particular 2 columns to the data frame that I get returned after this particular call. Right? It's really compact, right? But you can actually string them together just like any object-oriented. It returns you a particular data frame, and then you can actually use APIs on that to do width column and then another width column, and Spark will parse that. And I'm defining my watermark to be 1 minute. Even though I don't have to do that, I'm just going to go ahead and do it, so it knows that. So I'm going to go ahead and read that particular stream. Any questions on this? Are you guys doing it on your laptop? It's working, eh? Lovely. Yeah.
Does it support protocols other than JSON and
Yeah, I mean, the question was that does it actually support protocol buffs? Now, some of the RPC calls that Spark uses always uses protobuf. So underlying, the RPC calls is using protobuf. So we actually use that. Now, why did it return so fast? Huh? It's a transformation. Right? Remember, transformation are lazy evaluated. Right? Nothing is happening over here because you haven't created an action. Right? You're just telling Spark, read from this particular stream. Here's all my things that you actually need to get your job done. And then return me back your input. And what the input will look like is this, right? Which is what my schema is. So I've done that. I'll only launch that when I do this, right? So at this point, what I've done is I've taken my input file, right? I said, go ahead and now write using format Parquet. My option path is where the output path is going to be, so I'm storing something on a Parquet file. My checkpoint is where my checkpoint is going to be. My output mode is just append everything, right? And my query name is going to be something called devices. And when I have a query name, I can sort of, say query.stop, just like socket.close. The query name is a handler that comes in that has API calls to it that I actually could do. My trigger is every 5 seconds, execute that job and do it. And then when I do that, this is now running continuously. It's going to read one file at a time. It will do the processing. It will go to the next file at a time, one trigger at a time. And because it keeps track of the M time, it will go in that sequential manner. And this will tell me what my input rate and output rate is. And this is the batch, how long it actually took to do one trigger. And if I go to this particular file system, which is my output path, I'll see these things are being updated in real time. So when you hit shift control, which is going to execute the next cell. This is now actually running in real time. And you can actually see that. These are all the Parquet files it actually created, which has now been transformed with 2 additional columns in it as well. Now you can do a lot of transformation over there. Like, let's say you actually wanted to create a device of only a particular type that you're interested, you could actually do the filter in your data frame and then just filter out the devices that you care about. Or if you wanted to just filter out by the signal strength, then you can equally do that at the same time. So this would be something that you actually do that. Now this is actually happening in real time, right? We are still processing one file at a time. We got about 100 files, 1,000 files over here. And now here's the great part. Remember I was talking about continuous application? I'm going to go ahead and create a temporary table from my input frame that's actually come in, and I'll create a temporary table using this particular data frame API. So go ahead and create an input temporary table called Parquet sensors. And the reason I want to do that is because I'm able to query certain things. And if you're an SQL guy who will actually do that, hold on, I'll answer the question. I can do that. Yeah, go ahead. Yeah. And now, since I've actually created a temporary view, this is not actually a table, it's just like a temporary view, I can use SQL queries to do that. Now remember when we had our diagram in the continuous application, I actually had the streaming data coming in, I had an ad hoc queries. I can actually do the ad hoc queries over here, right? So I can say, go ahead and select everything from here, from my Parquet sensors, which is the table temporary view that I've created, where my device ID is of sensor type and device type is this, and I'm just going to go ahead and query that. Now this is going to run continuously as well, right? So now I have two streams running continuously. One is reading the data, transforming it into the Parquet file. The rest one is reading from the Parquet file, creating a table on it, and now I'm doing a filter. Right? A lot of things are actually happening, but this is all running continuously. Right? That's the beauty of it. And when I display it, this is what it is, right? This is the current time. This is my signal trend. Remember, I changed the data. I said my input file should be this, and my process time should be that. And these are my device IDs, and these are the only types that I get. String type is of type D or type A. Now, what about if I actually want to do group by? I want to do some aggregations. I can actually do that at the same time. So we got a couple of things actually running. Now, one of the things that we have to worry about when you're actually doing group by operations or when you're doing, order by is Spark actually has a default parameter of shuffle partitions of 200. So when you're dealing with small files and when you run a particular job and when you do a group by certain, value, if you look at the jobs, you'll see 200 tasks being created. And you wonder, why is it creating so many tasks when my file is so small? It turns out that when you do an order by, you have to do a shuffle. And it's going to create 200 partitions to do the shuffle by default. Because Mate said, well, they were sitting around at the table. They said, what do you think our default partition should be? And Mate said, I think 200. It would have been nice if he said 42, the answer to the universe. But he decided to go with the 4200. Not even a multiple of 42, but he said 200, right? And we're stuck with it. And here's the irony. The irony is that nobody knows what the bloody hell this thing does. And so when people stumble on it, it's not even documented, right? That's the painful part of it. So now it has sort of come to the prominence, so we normally mention that in any of the tutorials. So what we do is we take the shuffle partition and bring it down. So now you only have, a small partition to shuffle. Otherwise, you'll have 200 partitions or maybe like 2 files or 2 entries, and you're just having a lot of bandwidth data. But when you have large files, then the shuffle partition actually makes sense because now you have a lot of parallelism going on. So when you're going to do that, when you're going to create another view, now we're actually reading of a Parquet file from that maximum trigger 1, and my watermark to be 1 minute, so I don't care about, I want a little more latency. And I'll create another sensor table view. And you ask me, Jules, why are you creating all these tables? What is for? It was the whole idea of demonstrating that you write those things in a continuous manner, so you don't have to create all this multiple. You can actually do that in one notebook, and then you can actually go in and sort of create dashboards like this, where you can actually show you in real time what's happening. Anyway, we'll get to the dashboard later. I got a few more minutes left. right, so we're going to do that. And then we want to find out what files are being actually processed from the Parquet, and we'll do that. And the reason we actually set the partition one is because we're doing an order by here. We're doing a group by. We're saying go ahead and select input file and process file, group them by input file name. So I want to know, how many of those devices were in that particular file, and what was the process time? When did they actually hit the system? And count them, and then order by process time in a descending order, right? This reads and sounds like SQL, right? Because DataFrame was built on top of Spark SQL to give you the DSL and the familiarity and the intuitiveness of Spark SQL. So I run this particular thing, and here I am now sort of counting. Now, each file has actually 100 devices, so it actually makes sense that we actually done that. So all these things are actually happening, and you probably want to say, well, how much data is actually coming through? So I can do select count on my sensors to find out how much of that is. And this is all like happening in real time. Things are coming in, you're processing, you're writing it, you're making queries interactively. So you got some guy who's actually making interactively. Now normally these are temporary tables, but this could be permanent tables that other people can have access to. Yes? How often the data gets written to? Well, if it gets written to as soon as it's actually read, but the trigger is 1 minute, right? So every time you actually, the query gets executed, it just writes every 1 minute. Well, when you say write, you're actually using it gets translated into the unique file system write, if that's what you're asking. Because all this particular code gets translated in RDD, and the RDD is doing the write. It's using the low-level write APIs, which is the write input HTTP format to write to the Parquet file. In this case, it's going to use Parquet writes to write to the particular file. So it's going to do the Parquet, write the metadata, write the successful, and depends on the data source API, right? My data source over here is Parquet, right? It's going to translate into the API calls for the Parquet data source, and I'm going to call the native Parquet to go ahead and write those things using Parquet. And however Parquet is implemented, I don't care, right? But it's up to the Parquet. If Parquet is actually written in C++ and is running natively, and we have linked that particular library as part of it, it's going to write accordingly. And then once I actually have the data sensors, what I have now is the ability, we got count 440, that we are right there. And now I can actually use this interesting query that I can actually select everything, device type, find out the minimal strength, find out the maximum strength, what the average signal length is. These are the things that you actually normally deal with IoT devices in a very continuous manner, so you can actually do some monitoring and so on and so forth. And how are you guys doing on your community edition? It's a bit slow? Are you on this particular sale or you're up above? Oh, you're on 34? You're following it. Love it. And you're seeing this particular diagram being updated? Do you see the table? Yeah. And so once you actually have that, this actually makes, you can actually make really complicated dashboards, right? You can actually do this and put on a dashboard, and this could be in the NOC. People will actually look at it. You can actually beautify it quite a bit, but the whole idea is that you can actually create dashboards, so those can then be exported as HTML, and they get updated in real time. So people can actually see it on a dashboard somewhere that things are happening. And we use it internally a lot with this, and we got tons and tons of jobs running. We monitor a lot of stuff. And this is quite useful, quite insightful. And we're eating our own dog food at scale. And now actually I want to find out a little more about devices. I want to find out what kind of devices are coming in every 5 seconds based on my event time, right? As event time is progressing, I want to find out what kind of devices are coming in 5. Yes? This one? Yeah. How does it generate what? I can't, do you mind using the mic? Right. Oh, okay, yeah. So, yeah, the good question. The question was that how does a SQL query update this particular data frame, right? What's actually happening over here is that just this magic command over here, right? This is a magic command that you can actually execute in a cell. It's saying in this particular cell, go ahead and execute an SQL. When you do an SQL, it returns the data frame, right? But internally, we take the particular data frame and we just display it using the display command. So you don't have to specify. Yeah, in the notebook, yes. Yeah, it's already returned the data frame, and then you can actually use any of these plotting ways to change that particular plot, right? I can actually do that differently. And my plot options could be I want that as a pie chart, or I want something else. So that's how we actually use that. But by default, the question is that when you do an SQL query on a table, it returns back the selected query based on the filters that you provide. How does it display that? Internally, we just take the data frame and display it, right? Just like we do a display over here. And display is like, dataframe.show. Right? That is the open source one. Over here, we have an HTML version of display. So when you do a display data frame, it gives you a nice tabular way. It's easy to look at. It's like a spreadsheet. Right, so this is actually happening in real time. Now we actually want to take our devices and group by window to say how often how often the devices are coming in based on time, and then create another table. So we got lots of tables over here because people are just looking at tables all their lives. And I'm going to go ahead and create an SQL query, and to answer your question, this will actually return a data frame which is going to be displayed on as it is. There might be another query you actually want to do. You might want to say, go ahead, I'll answer.
So we have actually created a variable called query, which handles to that industry query. But essentially, we are not using that object anywhere in the notebook.
I'll show you at the end. I'll show you.
Implicitly, looks like that automatically the SQL figures out that it has to.
Yeah. What happens is that when you're writing Python, in those parentheses is very Pythonic to actually return you an object, right? And it doesn't display over here, but whatever that object is get fed to display, and then display knows that. Now at the end, I'll tell you how to show you Python trick to tell me all the queries that you actually created, and show them what they are and what to do with them. And you'll see when I do the cleanup, you'll see that towards the end. But if you're very curious, you can go all the way to the end, right? And then this sort of gives me the ability to sort of find out, all the signals, all the devices that have come in less than 5 within the last, any devices that actually have come in that particular count, which is less than 5, which means that there's something wrong, right? So I can monitor that. And so this over here is telling me, this is my start time, this is my end time, my device ID was this, and there's only one device that has come in. So I'm just curious to find out if I'm trailing behind something. And remember, this is an exploratory way, but you're doing all this in a very continuous manner, right? You're using structured APIs to actually do that. You might do it slightly differently when you go into production. What if you actually want to monitor this thing, right? What if you actually want to have the ability to say, well, I found out from this particular window, from this particular query, that there's something dodgy happening, and I'm missing some signals, so I want to monitor something. So there is a way to actually provide what we call, for each row that you actually find out in your particular query, go ahead and do something with that. There's also another routine called for batch. And this is very typical if you're running Ganglia, if you're running Kafka, if you're running those things. You want to monitor your signals that are actually coming in. And one way to do that over here is I can actually find out, for example, all my lost signals. These are all my lost signals that actually haven't come in my count is actually showing me less than 5, and I was expecting more than that. So what I can do is I can take my lost sense of signals, and I says, go ahead and do a write stream somewhere. Use the output as complete. Take everything that you actually seen in that particular way and just dump it. And then use this for each method, and then take this particular function and execute on each and every row. Right? So what's actually happening over here is I define my function called for each. Go ahead and print this alert right now in the log. But this could be something that you might say, go ahead and put it on a Kafka topic. or send a REST request to a pager duty alert that somebody actually gets waked up in the middle of the night, and it might blame you the next day or something. But this is the way you can actually monitor things in real time too, or put it on a dashboard, or send it to your grandma or something like that. So that's what this particular part will do. That will create one row at a time. And then if you go to your Spark UI and click on the master and you look at the standard error, you will actually get this particular row messages being printed in real time, right? But ideally, you would probably send it to the ganglia, right? Or you would send it to some monitoring utility or robot or data robot or something, where it's going to create a dashboard. So there are various ways to actually write continuous applications, the ability to do that. Now, I have 2 more notebooks, and I think we're out of time, unfortunately. And I urge you, and I really implore you, that you have the access to the spreadsheet, the reference document that I gave you. Import those particular notebooks, create a particular cluster, run on it. And you can send me questions or you can send me concerns anytime. I'll put my details over there. But these are some of the challenges. If you really feel like challenging after a couple of pints at the party, go home and try this out. It might put you to sleep, but you might say, yeah, Jules, send me an email. Look what happened here, right? I think that query was shit. I can do much faster than that. Check this out, right? I've got those emails that not only I've got DM messages at 3 a.m. in the morning after I did my workshop in PyDat Miami. Say, hey, your query sucks. Check this out. I can do this far more better. I say, yeah, I'll incorporate that next time. Yeah, go ahead. Yeah, there is. Where did my? Yeah, hold on. Okay. You see this over here? This particular command? Spark stream returns you a handle to the Spark query manager. Right? Once I get my query manager, I can use list comprehension to say, go ahead and get the queue name and print out all the queue names. Try that out when you get home. And then you can use this. Go ahead and actually use the list comprehension to get each and every query that I actually have, and then go ahead and do a stop. You got it? Right. So just cut and paste and run that. Yes? On Databricks Community Edition, you have no choice but run with smaller data. Yeah, so what you do is you do a cleanup data, just remove all the file descriptors and you'll be fine. Okay? Yeah, just clean up your /temp-rm or run that setup cleanup data and it'll actually run that. Okay, so the window is the implicit function in structured streaming that keeps track of 2 things: the window start and the window end. Right? That's built in. Right? Any other questions? Don't forget to give me a negative score on your application. That I made you suffer, but at least I gave you cure to insomnia. When you go at night, you can actually go to sleep. But this was a summary. And if you actually want to get in touch with me, I'm on Twitter. Send me a DM message, 4 a.m. in the morning, I'm awake, because I'm debugging a structured streaming that some student sent me. And connect me on LinkedIn. I'll be more than happy to share any knowledge that I have with you. And if I don't have the answer, I won't pretend that I do have. I'll go find out, and I'll answer back to you. And if you guys are having meetups, you want me to come and give a talk, I would love to do that. And I hope you actually enjoy. If this was more time, we would have actually done all the 3 different continuous application. One is actually running. The second application is, I urge you to actually try that. We're taking fraud detection data from a place in Italy, and we're detecting whether this is a transaction is fraudulent, and we're doing it in real time. So we create the particular model. We take data coming in from real time, and we predict whether this is a fraudulent motor or whether it's not, using logistic regression. So I try that. And the third one is that I think the gentleman over here was asking me about watermark. That actually illustrates exactly what watermark is, what window functions are. I didn't have a time to do that because we just don't have enough time. But this is normally, like I said, an all-day affair. But yeah, I've documented all those in Cell. One of the great things about Notebook is like a book. You're actually reading that thing. That's why it's called a notebook. You can actually put explanations in there. And if you have any questions, please ping me, okay? Thanks a lot for coming, and enjoy the rest of the Spark Summit. And see you tonight. We should have some beers together.